So here's a very interesting physics problem, which was actually given to the ninth graders. So those are students who are around 15 years old in 2024 at the Romanian County Physics Olympiad. And the problem itself is not particularly difficult in terms of the mathematics involved, but there is a lot of work to do, as you'll see. So let's read the question and let's see how we would approach it. So this was problem one. In total there are three problems, or three subjects as they're called, and the first one is on kinematics. So it says that a body moves from point A to point D. So it starts here at point A and it ends up here at point D. Only under the action of a linearly increasing horizontal force over time and gravity. Oh, by the way, so I obviously the original paper was in Romanian, but I had to translate it, and I did so with ChatGPT. I think the translation is pretty good, but if there are any weird things, then that's the reason. Anyway, so we know that this object is, throughout its path from A to D, it's subject to two things. One of them is this, that's the key, linearly increasing horizontal force over time, as well as gravity. Initially, we know that the body is at point A on the horizontal platform AB, suspended at a height h, which is 80 meters above the ground. And at the initial moment, which is at 0 seconds, the velocity is 1 meter per second and the acceleration is 2 meters per second squared. Okay, so this is all we know for now, and we have to sort out a couple of things. So the first thing is this. So determine the velocity of the body at point B, so that's here, at t2 equals 4 seconds after the motion starts, given that at t1 equals 1 second, the body's acceleration is a1 3 meters per second squared. Before I start, I should say that I think this is a good problem for anyone who's doing physics in high school and is preparing for final high school exams in physics, because this problem tests your understanding on multiple aspects, and I think it's really good in that regard. Now, the closest topic that this is similar to, I would say, is SUVAT. The only problem with that is that we can't really use SUVAT in this case because we don't have a constant acceleration. So we know that the acceleration is changing because, well, we're told at two different points. So we know that the initial acceleration is 2 meters per second squared, and after 1 second the acceleration is 3 meters per second squared. So we have to see what's happening with that. So to figure this out more quantitatively, we're going to use the fact that the force that we're dealing with is linearly increasing, and this is key because this happens from A to D, but I think in the first in the first 4 sub questions we just have to deal with this path going from A to B. So in any case, during the path from A to B, we know that the horizontal force, this Fx, is linearly increasing, and we know that if this is linearly increasing and there's no friction or anything like that, then the acceleration, the horizontal acceleration, is linearly increasing as well. So I'm going to say that Ax is linearly increasing. So, well, how do I know that? Well, it's pretty simple. I know that the relationship between acceleration and force is that acceleration is force over mass, and mass is, it's a constant, so it doesn't really affect anything else other than just a couple of values. But if the force is linearly increasing, then so is the acceleration in x. And we don't really know anything beyond this, so what I'll say for now is that the acceleration ax, let's call it, is going to be, or let's just call it a, just to save some characters. So I'm going to say a of t, so that's acceleration with respect to time, is equal to kt plus b, right? So this is the most general way of writing a linear function, right? Which is a function of t basically. So I have my t as the independent variable, I have k, which is the slope, and I have b, which is the y-intercept. So at this point we can actually find k and b quite easily, because we know that at the initial time, we know the acceleration at the initial time, and we know the acceleration after 1 second. So this gives us two equations and two unknowns, right? So we can say that at time equals 0, so a of 0 is equal to b, right, which is equal to 2 meters per second squared. So the other thing is a of 1 is equal to k plus b. Yeah, I'm just replacing t with 1, which is equal to 3. Yeah, this is what we know here. So we know b is 2, therefore k is just equal to 3 minus 2, which is 1. And we should write the units for k as well, and I believe those are going to be meters per second to the power 3. That's the only thing that makes the dimensions work in the end. So we have that acceleration, so a of t is going to be equal to t plus 2. And this is going to be meters per second squared, and there we go. So as you can see, this acceleration is changing with respect to time, so the Suvet equations won't really work in this case. This is kind of like a problem that is Suvet on steroids, as I like to call it. And in 9th grade, students don't learn anything about calculus, so they don't know anything about derivatives or integrals, so it's going to be interesting to figure out things like distances and velocities without knowing some further maths. But we'll try to solve it, because you know this was given to 9th graders regardless. So let's see what we actually have to do in part A. So we have to find the velocity of the body at point B, which is after 4 seconds after the motion starts. So we're being told that point B is at a certain distance from point A. We don't know how far it is yet, but we know that the object gets to point B after 4 seconds. So we have to find the velocity at that point. So the easiest thing to do, in my opinion, is to draw a graph. So what I'll do is I'm just going to draw the graph of the only function that I have, which is acceleration. Because if you can't do calculus, then you have to use the second best thing, which is plotting a graph and then figuring things out this way. So we know that this is 0, and we know that the acceleration after 1 second. So I'm gonna do this. So this is 1 second, this is 2 seconds, 3 seconds, this is 4 seconds, and then the acceleration is therefore given by this formula, so we can easily find what the acceleration is at any time, essentially. So the acceleration at 4 seconds is going to be equal to 6. It's as simple as that. So I'm gonna try to make this to scale. I won't be able to do this every time when I draw the graph, when I draw graphs in this question, for reasons that will become apparent. Let's put some units. So this is 6, and we have this. So after 4 seconds, the acceleration is 6, right? Because remember, a of t is equal to t plus 2. So a of 4 is equal to 4 plus 2, which is 6 meters per second squared. Okay. And we also know that the acceleration at the beginning is equal to 2. So the acceleration doesn't actually start from 0, it starts from this value here. So this is 2. Okay, so the graph of our function is going to be equal to this. So, nice linear function. And using the graph, we can now figure out what the velocity is after 4 seconds. So we're trying to find what is the velocity at time equals 4. If we know everything there is to know literally about acceleration. So this is where we use the, we use the definition of acceleration as students learn it in the 9th grade. So we say that the acceleration, the tangential acceleration in this case, is delta v over delta t. Okay, so then we know that if we rearrange this, we would get that delta v is equal to a delta t. And unfortunately, as I mentioned earlier, we can't actually use suvat because acceleration is not constant. But we know that we can make use of the other thing, which is the area under the graph. So we know that the change in velocity, so the delta v, is equal to the area under the graph. Right? Because we know by using further maths that the velocity is the integral of a dt, and the integral of a dt is the area under the graph. But thankfully, in this case, the area is relatively straightforward to calculate because it's a trapezium, and we can find the area of the trapezium. So that would be equal to the small base, so that's equal to 2, plus the bigger base, which is equal to 6, multiplied by the height, which is 4, divided by 2. So we can cancel those out, and we get 16 meters per second. So this is the change in velocity from the beginning to end. So we can say that v4, that's velocity at 4 seconds, minus the velocity at 0 seconds, is equal to 16. So we can find the velocity after 4 seconds as 16 plus v of 0, which is 16 plus. So we know the velocity after 1 second is equal to, the velocity at the beginning, not after 1 second, is equal to 1. So this is going to be 17 meters per second. And that is part A done. So we found the velocity of the body at point B. Okay, so the next thing to do in this case would be to obviously move on. And for part B, we have to figure out the following. So we're told that for any moment of time t, which is between the initial time being 0 seconds, yeah, it's given here, and t2, which is 4 seconds, establish the expression of velocity as a function of time. So we have to find v as a function of t and plot the corresponding graph. So we're not going to bother with plotting the corresponding graph because we've done that already pretty much. So what they want in part B is they want us to find an expression for the velocity as a function of time. So we've already found the velocity at the end after 4 seconds, and now we have to find the velocity at any given moment in time. So we're going to use exactly the same approach. I'm going to take this, I'm not going to draw it again, and I'm going to make use of it. So I'm going to say, okay, I'm going to take a certain arbitrary time t. So I'm going to take a moment of time t here for no particular reason. And I know that a of t is equal to t plus 2. So if I look at the corresponding y coordinate, this value here is going to be t plus 2. And to find the velocity, we're going to do the same approach as before. So we're going to look at the area under the graph. Now this time, we're going to look at this area, which is going to be delta v equals. So we have, as usual, we have the area of the trapezium that we have to find. So it's this side, which is 2, plus this side, which is t plus 2. and then this is multiplied by the base, which is t, divided by 2. Okay, so this gives us 2t plus t squared plus 2t again, divided by 2. So we end up with delta v being equal to t squared over 2 plus 2t. Now, this is the change in velocity, it's not actually the final velocity. To find the final velocity, we have to write delta v more explicitly, so that's v of t minus 1, which is t squared over 2 plus 2t. So the velocity as a function of time is t squared over 2 plus 2t plus 1, and that's it. And that's meters per second. So this is how essentially the velocity changes with respect to time. That's the velocity function, as they say. So, and I believe that's everything done for part B. Okay. C is quite interesting. So it says for the interval t from 0 to 4, estimate, and this is going to be a keyword. So they say estimate the distance traveled by the body on the AB surface during the first second and during the last second. Okay, so we're gonna try to understand why we have to estimate. So now that we have the velocity, normally to find the distance at this point we would have to integrate, but again this is supposed to be done by 9th graders who have no idea about integration, and the good news is that we don't even have to find the exact value of the distance, we have to estimate it. So again, I'm gonna do the second best thing, which is trying to plot the graph. So I'm gonna take this function and I'm going to try to plot it here. It's not going to be to scale, as you'll see, but we'll try to work with it regardless. Anyway, so we have that at the initial time, so I'm gonna write it here actually, so we can say that v of 0 is equal to 1 meter per second, and we know this from the initial conditions that we were provided with at the beginning. And we also know that v of 4 is 17 meters per second. Now, obviously, this is not going to be a straight line, right? Because there's t to the power 2, so it's going to be a quadratic. And it's going to look something like this. So we have 1 second, 2, 3, and 4. And the initial velocity is here, and yeah, unfortunately I don't think I can go 17 times higher, or 17.5 times higher. No, 17, yeah, it's 17 meters per second. So the final velocity is going to be this one. So let me put the units as well. Something like this. Let me try that again. Yeah, so we have the initial and the final velocity. Now this is going to be a quadratic, and also we could find, if we wanted, where the minimum of this quadratic is going to be, and this does have a minimum actually, but it's in the negative x direction, so we don't really care much about that. But the graph is going to look something like this kind of. Let me try that again. Yeah, more or less. Okay. Yeah, and that's basically v as a function of t. And now what we have to do is we have to find the distance traveled in the first second and in the last second. So we know that the distance traveled is the area under the graph, but we can't integrate. We're not allowed to integrate, or we're not allowed to, we're not supposed to know integration at this point. So we're going to draw a trapezium, and we're going to find the distance. We're going to estimate the distance in this way. So I'm gonna say that delta x1 is not equal to, but it's approximately equal to the area of the trapezium, right? So we know this side is 1 plus, then we know this side as well. So this one is the velocity after 1 second, which we actually don't know. So let's try to find it out. So the velocity after 1 second is 1 over 2 plus 2 plus 1, which is half, plus 3, which is 3.5. Okay, so we know this value here is 3.5. So we have 1 plus 3.5 times 1 divided by 2. And this is going to be 4.5 over 2, which is 2.25 meters. So this is how much the object travels in the first second, and we're going to do the same thing for the last second. So the last second is from 3 to 4. So again, ideally, we want to find the area under the graph, you know, which follows this curve, but we can't do that. So we're going to take the approximation, and the approximation is essentially the area of this trapezium, which should hit 4, but anyway, yeah, we're gonna leave it like this. So this is going to be delta x 4, I guess, and it's approximately equal, it's not exactly equal, to the velocity at 3, which we also don't know. So let's try to find it out. So the velocity at 3 is equal to 9 over 2 plus 2 times 3 plus 1, which is 4.5 plus 6 plus 1, which is 7 plus 4.5, so that's 11.5 meters per second. So we have 11.5 here, so that's 11.5 plus 17 times 1 over 2, and I'll have to use my calculator for this one. So we have 11.5 plus 17 divided by 2, and we get a final answer of 14.25 meters. Yeah, approximately. But the question was asking us to estimate, and we've done exactly that. And yeah, this is how you do it in this case. So we'll consider part 3 to be done. Okay, now for the next 2 parts, we are leaving the horizontal surface. So we know that at point B, the horizontal surface ends and the body is launched horizontally with velocity v2. So from this point onwards, this becomes a projectile motion question, but it's not a standard projectile motion. Instead, it is, well, it's an upgraded version of that in a way, because it's not, the motion is not under just weight. There's also this horizontal force which is acting on the object all the time. So regardless, the object is launched at B, and then we have to calculate the radius of curvature of the trajectory at point C, where point C, so we know the object reaches point C 1 second after detaching from the platform. And here we have an explanation of what the radius of curvature is. So they say the radius of curvature at a given point is the radius of the circular arc that best approximates the trajectory in the vicinity of that point. So anyway, we're going to assume that you know, we're familiar with that, and we're going to try to find what is the value of that radius of curvature at that point. So let's try to figure out what happens at point C. point C being here. So I'm gonna draw the diagram, I'm gonna redraw the diagram, and I'm going to have my object like this, and so this started from this point, and it started with a horizontal velocity, which I'm going to call ux, of 17 meters per second, like this, because that is the velocity after 4 seconds. So we found that in part A. And then the object is traveling along this path, and it's going to land at point D, where point D has the same horizontal, well, it's at the same level as as the bottom of the platform. So we know this has a height, which we're going to call h, which I believe was something like 80 meters. Yeah, so this is 80 meters. And then our coordinate system, I'm gonna draw it here like this still. And point C is going to be somewhere here. Okay, so here's what we know. So we know that the initial horizontal velocity is 17 meters per second, and then there is another horizontal velocity here, which we don't know. Now, remember, this is not pure projectile motion, because the object is not acted upon just by its weight. There's also the horizontal force, which changes the horizontal velocity component. So Vx and Ux are not actually equal to each other. Okay, now I'm actually going to draw this in a slightly different way. So I'm going to draw the velocity vector itself like this. And then I'm going to say that this is Vx, and this is Vy, like this. Okay. Right, so we also have to somehow use an expression that has the radius of curvature. And to do that, we're going to have to look at what's happening perpendicular to the trajectory. Because perpendicular to the trajectory, we have this component of acceleration, which is essentially the normal or the centripetal acceleration. And we know that the centripetal acceleration is equal to v squared over r. And it's this r that we have to find, and r is v squared divided by this centripetal acceleration. So let's try to figure out a couple of things. Let's try to figure out the things that we can find. The first thing I would say to do is to find Vx. So we know that Vx of t has the formula that we have here, which is t squared over 2 plus 2t plus 1. Now I'm going to call it Vx from now on, because there's going to be a horizontal and a vertical velocity component, and therefore the velocity after 1 second, that's 1 second after it left the platform, means that we have to find the velocity at not at 1 second but at 5 seconds. Why is that? Well, because it took the object 4 seconds to go from here to here, and then it took the object 1 more second to go from here to here. So the total amount is 5 seconds. So Vx of 5 is 25 over 2 plus 10 plus 1, and that is equal to 12.5 plus 11, which is 23.5. So we figured out that Vx here is 23.5 meters per second. Okay, so the next thing is to try to find Vy, and finding Vy is relatively straightforward. So we're going to say that Vy is equal to Uy, right? Where Uy was the vertical velocity here, and then minus g times tau. So minus g because gravity is acting downwards, and tau is 1 second. Keep in mind we're not using 5 seconds here because the object only started falling after the initial 4 seconds. So this tau is just 1 second. So we know that Vy is equal to 0 minus 10 times 1, which is minus 10 meters per second. So the minus means that it's falling, right? It's acting downwards. So I'm gonna just call it 10 meters per second, right? I just care about the magnitude when I find angles and things like that. Okay, so that's essentially what we have in terms of velocities. So the other thing we need really is we need the acceleration, well, the total acceleration. So I'm going to redraw the object at that point, and I'm going to make the diagram a bit more clear. So we have the object like this. We have the velocity acting, I try to use straight lines instead. We have the velocity acting something like that. Then we have our Vx, we have our Vy, so we have Vx going this way, we have Vy going this way, so we have Vy, we have Vx, which is, so this one was 23.5 meters per second, this one was 10 meters per second, and then we also have the acceleration components. So first of all, we know that the gravitational acceleration is going to equal 10. So the vectors have the same magnitude basically. So I have g, which is 10. Okay, and we also have, or we also need the horizontal component of acceleration. So we know that acceleration as a function of time is given by this, which is t plus 2, and to find the acceleration at this point, it's essentially the horizontal acceleration after 5 seconds. So that's 5 plus 2, so that is 7 meters per second squared, like this. So this is essentially what we're dealing with. So this is AX, which is 7 meters per second squared. Okay, so now what we need to do is we need to find the normal component of the acceleration. So, in other words, we have to find what this component of g is. So this would be equal to g cosine of theta, where theta is this angle, which is the same as this angle, yeah. And then the other component is this one, which is, so this would be ax sine of theta, right? Because that theta is also that theta, and those things combined would give us the normal or the centripetal acceleration. So ACP is g cos theta minus ax sine theta. Okay, now how do we find theta? Well, we use the velocities. So we can say that tan theta is equal to Vy over Vx, which is 10 over 23.5, and that gives us a theta value. So the angle should be equal to, let's have a look, so 10 divided by 23.5, is 23 degrees, approximately 23 degrees. So the centripetal acceleration therefore is going to be equal to 10 multiplied by cosine of 23 minus ax, so ax is 7 times sine of 23 degrees, which is, well, we have to calculate this, so cos of 23 is that, times 10 minus 7 sine of 23. Yeah, so I get approximately 6.47, and that's meters per second squared. Okay. Yeah, and that's essentially it. Okay, now that we have the centripetal acceleration, we can find the radius finally. So centripetal acceleration is v squared over r. So r is v squared over centripetal acceleration, and v squared is just vx squared plus vy squared divided by centripetal acceleration. So this becomes, so vx was 23.5, so that's 23.5 squared. Vy is 10 or minus 10, depending on your convention, and the centripetal acceleration is 6.47. Right. Okay, so let's try to add everything up, and I get 100.8 meters, or approximately 101 meters, as the radius of curvature at this point. So in other words, the way to interpret this result is that if you, might be a bit hard to draw, but I'll try. So if you draw a circle which is tangent to that position, and the circle is pretty big, but the radius of this circle from here to here, or from, it could be anywhere on the circle, so this radius would be 101 meters approximately. That's essentially the idea behind this part of the question, and that is sorted. And finally, we have one more thing to look at, which is to determine the angle between the velocity and the acceleration vectors at point D. Okay, well, we know what point D is. We know that point D is the point on the ground. So to begin with, I would try to figure out what is the velocity, first of all, at point D. So we can figure out what the horizontal velocity and what the vertical velocity is. We don't know the time of fall yet, but we know that the object starts from a height of 80 meters with no vertical velocity, and then it reaches the ground at some point. So we can say that h is equal to 0 minus 1/2 g t t subscript t squared. So that's like the total time, pretty much. That's the time, well, I should say this is the time the object spends in the air. So realistically, I should call this tau total, because tau is actually the time that the object is in air, and this is squared, of course. So if we rearrange, we get 1/2 g this is equal to h. So the total time is the square root of 2h over g, and let's see what we get. So this is 2 times 80 divided by 10, which is 4 seconds. So the object is in air for 4 seconds, which is a good piece of information, because we can find everything else from this, right? So we can find the vertical velocity component, so we can find Vy, which is equal to minus g times this time, which is going to be minus 40 meters per second. Then we can also find what is the horizontal component of velocity. So Vx of total time, this is going to be Vx at 8 seconds, right? Because the object spends, so it takes the object 4 seconds to be on the platform, and then 4 more seconds for it to land, pretty much. So we have to find Vx at 8, and this is going to be equal to 1/2 times 8 squared plus 2 times 8 plus 1, which is equal to 32 plus 16 plus 1, which is 49 meters per second. Okay, so those two together, they will tell us what the velocity is just before the object lands. So we found everything there is to know about the velocity, and now we'll do the same thing about acceleration. So let's try that. We know that ay is minus g, which is minus 10 meters per second squared. So that's pretty easy. And then we do the same thing with ax. So ax is going to be ax after 8 seconds from the beginning, which is going to be 8 plus 2, and it's going to be 10 meters per second squared. So funnily enough, the horizontal and the vertical components of acceleration in this moment are equal in magnitude. Okay, so that's sorted. And I think it's the easiest thing to do at this point is just draw a diagram to see, what's actually going on at that point, at point D, just before the object lands. So let's try that out. So I'm gonna draw the accelerations first. So I know that ax and ay, I'm trying to keep this to scale roughly, so they are equal in magnitude. So ay is 10, ax is also 10, right? And now we draw the velocities. So for the velocities we have where was it? So the horizontal component is 49, almost 50, and this vertical one is minus 40. So this is 4 times longer than ay. So 1, 2, roughly 3, 4, something like this, more or less. Yeah, actually I don't think I can afford to keep it to scale. I mean, I could actually, if I redraw this somewhere else. So let me try again. So let's do it here. Let's do it like this. So we have the acceleration components. So we have ay, and then we have ax, and then we have the velocity, the vertical velocity, which is 4 times longer. So we have 1, 2, 3, 4. Let's say that's not good. 1, 2, 3, 4. This is taking longer than it should. And then this one is about 5 times longer, so it's something like this roughly. Okay, right. So this is Vx, which is 49 meters per second. This is Vy, which is 40 meters per second. This is Ax, which is 10 meters per second squared, and this is Ay, which is like this. Okay, so now we have to find the angle between the vectors. So the acceleration vector is like this. Yeah, and this is pretty nice and easy. We know this angle is 45 degrees because this is an isosceles right triangle. And then for Vx and Vy, we have this going on. So we have something like that. So this is the velocity vector, and this is the, let's put the vector notation like this. Okay, so The other angle we should find at this point is this angle right here, which I'm going to call it alpha. And we know that tan of alpha is equal to Vx over Vy in this case, which is 49 over 40, which is equal to, I'm going to try to find the angle straight away. So 49 divided by 40 is, is going to give us an angle of approximately 50.7 or 50.8 actually degrees. And the angle we have to find is this one. So it's the red angle that they're asking for, and the red angle is, let's call it gamma, for example. So gamma is equal to alpha minus 45, which is 50.8 minus 45, which is equal to, well, I should say approximately equal to, but you get the idea, 5.8 degrees. And that's it. So the angle between acceleration and velocity is 5.8 degrees, and that is it. So pretty long question. Obviously, in an exam type situation, it would take much shorter because I was explaining what I was doing at each step of the way. And I'm sure there were kids out there who did this pretty quickly and got full marks as well. So yeah, overall I think this is a neat question for anyone doing physics and preparing for some kind of final exam. I believe if you're able to do this question in particular, you can assume that you have mastered quite a lot of concepts on kinematics, because it does test you on a lot of stuff. But in any case, that's the end of the question.